Welcome to the first lecture video in Unit 5. It's titled Simplifying Your Life. The quote that we have is, "Today's scientists have distributed mathematics for experiments, and they wander off through equations after equation and eventually build a structure which has no relation to reality." And so it's from Nikola Tesla. What we're going to be doing is we're going to be looking at chemical equations and trying to make sense of some of the symbols. Students will use chemical symbols to express chemical reactions. So talking about chemical reactions and the symbols that go along with it. Convert between written description of a reaction and chemical symbols, and then apply the law of conservation of mass to chemical symbols. So jumping right into it, what we already know coming into this. Evidence for chemical changes include changes of state, changes in temperature, and change in color. And what else we know is we also know how to name. We see we have sodium chloride right here, and then we have the equation, the formula for sodium chloride. What we should have picked up in the lab, the law of conservation of mass applies to chemical reactions, and adding mass to one side will produce more mass on the other side. And so chemical reactions act a lot like this scale over here. If we have more reactants, we put more stuff on this side, then there will be more product made on the other side. And so that is the law of conservation of mass. Equations. Now, equations are used to simplify your life. We try to bring a ton of information, very big pieces of information, and bring them down to very small, manageable chunks. Equations use symbol to represent things, and the relationship between these symbols is examined, and then equations only work if you understand the language of the symbols. So essentially what we're all saying with all of these things right here is this equation doesn't make any sense to you. You look at it and you go, I don't know what that is, because you don't know what the symbols mean. Okay, and so this took a very big, large piece of information and made it manageable, put it down to something that can be written in a single line, and so therefore you can use it. And that's what chemical equations will do as well. Now, chemical symbols, chemical equations use the elemental symbols. We find these elemental symbols on the periodic table. Okay, and for example, carbon has the symbol of C, oxygen has a symbol of O. So carbon dioxide means we have CO2. And we see the equation here. What we could say by this is a carbon, two oxygens produce carbon dioxide. This is not actually the correctly written formula for oxygen. We know it's a diatomic, but we'll get to that in a little bit. Our first question, what is the fundamental question? A1, what is the chemical symbol for sulfur? So we look on the periodic table. Sulfur has a chemical symbol of S. And so we see that on the periodic table, see that it has an S, and that is sulfur. Developing level question, what does the term CaO mean? So when we look at it, we look at its parts. The first part that we have Ca, which we look on the periodic table is calcium. And then we have the O, which is oxygen. So this is calcium oxide. And that is an ionic compound that we have, and that represents because of the calcium and the oxygen. Our next example, it says, what is the difference between CuCl and CuCl2? What we should recognize on this is that copper is in both of them, and we see that we have Cl, which is chlorine, is in both of them. Except on this, the first one, we only have one chlorine. On the second one, we have two. So when we're looking at this, we look at it and we say, well, why does that happen? Well, copper can have different oxidative states, different oxidation numbers. And so what we have to do is both of this copper, the first one is copper 1, the second one's copper 2. So when they went to crisscross, we have Cu, if it was plus 1, chlorine is minus 1. They crisscrossed, and they got CuCl. Now, CuCl2, that means we had copper 2. And so copper has different oxidative states in this, and so that's why we get different chemical equations. Looking at our mastery level question, it says describe the following equation using words. So when we look at this, we look at our very first part. We have copper 2 chloride is reacting with zinc, produces zinc chloride and copper metal. And so that's our chemical reaction below. Now, states of matter. We know the states of matter: solid, liquid, and gas. In any chemical equation, you must indicate or must include the state of matter when writing chemical symbols in their equations. Solid, liquid, and gases can only react if they are close in proximity to one another, meaning the molecules don't actually react unless they actually touch. So they have to actually bump into each other for a reaction to happen. So when we're looking at solids, solids are generally unreactive. Solids are indicated by the symbol S in parentheses, and the reason why they're unreactive is there's less opportunity for solids to interact, because the only atoms that are available to interact are the atoms, if we're taking this solid here, are the atoms on the outside. So it's not able to bump into other atoms, so therefore it can't react. Now, liquids, on the other hand, liquids are more reactive than solids. Liquids are indicated by an L. There are more opportunities for liquid to interact because all the atoms in a liquid can flow and they can bump into each other, and so they're generally going to be reactive, a lot more reactive than are solids. And gases, on the other hand, gases are generally unreactive. When we talk about unreactive gases, we are talking about the noble gases. We do have gases that generally react, that they can have reactions with, but those noble gases are unreactive. Gases are indicated by the symbol G in parentheses, and there is large opportunities for gases to interact because they're moving all around. There's a lot of space in between them, and so they can bump into each other. So as long as they are not a noble gas, we're going to react because they're going to bump into each other. Lots of opportunity for that to happen. Now, something that is aqueous. We can represent something that is aqueous. They're generally reactive. What it means, aqueous means that there are solids that are dissolved in water. Anything that is dissolved in water is considered aqueous. The symbol for it is AQ in parentheses. So if we put salt into water, we have aqueous salt. It's salt water, and that's what aqueous means. So our first fundamental question for this section, it says, what state of matter is the goal below? And so when we see it, it's in solid form. So what we would say is we put an S in parentheses. It's in solid form. That's the state of matter. Identify the state of matter based on the pictures below. If we're looking at this one, very, very rigid structure and very, very set and organized. So this would be a solid. And see how these are kind of flowing a little bit? That would be a liquid. So we have a solid and a liquid. Our next example, it says write an equation for the melting of ice into water. So when we look at this, we have water. We know that water is H2O. It's going from melting from ice into water. So the very first one would be a solid into H2O in the liquid state. And so that would be our equation for solid ice melting into liquid water. And our mastery level question: sodium chloride is dissolved in water. Write an equation for this process. And so we have NaCl in the solid form. And when we have this, we're just placing it into water, and so therefore we'll have NaCl, and now we just put AQ. And so we would say that it hasn't reacted with water because it's not really changing it, but it's just in that water, so it becomes aqueous. Now, chemical reactions. The elements, molecules, and compounds change in a chemical reaction. They change by the movement of electrons as valence electrons. The atoms can be rearranged to form a new substance. And reactions show the reactants, and this is a big thing. Reactants are what you start with. And equations show the products, and the products are what you end up with. Arrows in a chemical reaction. If it's an arrow, it separates the products and the reactants, and the arrows always point towards the product. And so reactants can proceed forward, and the arrow points to the right. So that arrow right there is a forward reaction, and reactions can proceed to backwards Okay, not forward 0, but backwards in reverse. And so that would be our reverse arrow here. And then reactions can move both directions. Arrows point both left and right. And so that would be a reaction that's going back and forth. And so we have all these arrows showing where the reaction is taking place. Now, catalyst can be used in a chemical equation. Catalysts will speed up a chemical reaction. Catalysts do not change the products or reactants. They're not involved in sense that they're not changing. When you'll still have your catalyst when you're finished. Enzymes are an example of a catalyst, and enzymes help replicate DNA but do not change the DNA. So you should kind of pick on that from biology. When we're looking at a chemical reaction, what we have our reactants, we have our products, and then catalysts are going to go above or below the arrow. And so when we look at this, this is how a structure of a chemical reaction will take place. So this reaction is moving forward because we see the arrow right here. Here are reactants, here are our products, and we have our catalyst above the arrow. Other common chemical symbols that can be used, when we say produces or yields, that means the arrow. We have our reversible reaction where we talked about those arrows. There's our solid, liquid, gas, aqueous. Catalyst, so that's an example of a catalyst, is potassium iodide. We would write that above the arrow. If there's a triangle above the arrow, that means that we need heat. And in front of the chemical formulas, so when we mean by in front of the chemical formulas, say you have NaCl, good old salt, say you had a number 2, that is a coefficient. Numbers in front are called coefficients, and those tell us how many moles of something we have. So translating from word equations into chemical equations, we can take a look at this. It says the student places hydrogen gas into a sealed chamber containing pure oxygen. A spark ignites the chemical reaction as seen in the combustion of the gas resulting in liquid dihydrogen monoxide. Well, taking this big piece of information and writing it down into a word equation, what we see is we have hydrogen gas plus oxygen gas produces liquid dihydrogen monoxide. Taking it even farther, hydrogen is H, oxygen is O, dihydrogen monoxide is H2O. And we see we have gas, gas, liquid. Now, the one thing we do have to pay attention to whenever we write chemical equations, we have to make sure that we remember Brinkelhoff, Brinclhof, and those guys are diatomics. So when hydrogen is by itself, you put a 2 with it. When oxygen is by itself, you put a 2 with it. Now, if you look, that oxygen is not by itself. It's attached to that hydrogen. That's why it doesn't have a 2. The reason why hydrogen has 2 is because of the way it's bonded. Okay? Diatomics have to be by themselves for you to write that 2. So looking at the fundamental question, it says to find each of the symbols below. So our first one, the arrow, means to produce or yield. The double arrow means it's a reversible reaction. We have a solid, a liquid, a gas, aqueous, which aqueous means it's dissolved in water. Above the arrow, that would be heat. This would be an example of a catalyst, and the number in front would be coefficients. Developing level question. Fill in the missing symbol in the equation below for the combustion of gasoline. So when we're looking at this, the symbol that we really need, the one thing that's missing is just a spark. We need the spark there to ignite that gasoline so it can produce that H2O, CO2. And so all we would do is we can represent the spark. Just put the triangle above, say it needs a little bit of heat, a little bit of energy to help the process along. And our next example, it says write the chemical equation for the following scenario. We have solid sodium. So sodium is Na, and it's a solid, so we put it in parentheses. Reacts with chlorine gas, Cl. We put a 2 here because it's a part of Brinkelhof, Brinclhof. Chlorine is a gas as well, so we put a G. Reacts to form sodium chloride. Which sodium chloride? Sodium is Na, chlorine is Cl. Sodium is +1, chlorine's -1 on the periodic table. We crisscross, and we get NaCl. And this would be, it says it forms sodium chloride. It doesn't tell us if it's a solid or a liquid or gas, so we just put NaCl. And our last example, it says write the chemical equation for the following scenario. The scientist heats a piece of solid magnesium in a Bunsen burner. The light produced continues even when the flame is extinguished. The metal disappears, leaving behind a white powder. Write an equation based on the description. So we have magnesium. We're adding a little bit of heat to it with the Bunsen burner. Okay, and we got to figure out what the other product is. Well, it's reacting, and this is what it doesn't tell us. It's reacting with the oxygen, the O2, in the air. And so this is a solid piece of magnesium. The gas in the air is oxygen and produces a powder, magnesium oxide, which is also a solid.